If you really stop and watch a bird in flight, it's pretty incredible. If you look closely, you'll notice their wings aren't just these stiff, static things. They're constantly warping, flexing, and adapting their shape to catch the wind perfectly, shifting seamlessly from these intense, high-speed dives to really gentle glides. Now, if we look at this through the lens of an aerospace engineer, that kind of biological perfection has literally been the ultimate dream for aviation for over a century. I mean, what if airplanes could change their wing shapes mid-flight, just like birds? Well, we aren't just dreaming about it anymore. Today, we're looking at a massive breakthrough that proves this is actually becoming a reality.
Welcome to today's Explainer. We are going to be breaking down some truly groundbreaking flight tests conducted by the German Aerospace Research Center, or DLR for short. They've been flying an experimental drone called Proteus, and it's equipped with something that honestly sounds straight out of science fiction: a shape-shifting wing controlled entirely by an artificial intelligence brain. We're going to reverse engineer exactly how this whole setup works, relying strictly on the data and insights from DLR's recent tests.
All right, here is our flight plan for today. We'll start with the Proteus drone test, move into the HyTEM technology, cover aerodynamics and efficiency, look at the adaptive AI brain, discuss fault tolerance, and finally wrap up with the flight results. Let's dive in. Okay, kicking things off with Section 1, the Proteus experimental drone. So to test a totally radical new concept, you obviously need a reliable testbed, and that's where the Proteus comes in. Proteus is DLR's uncrewed aerial vehicle, and it recently took to the skies at their specialized research facility over in Koststedt, Germany. Now, this wasn't just your standard run-of-the-mill flight test. This was the ultimate proving ground for a concept that fundamentally challenges how we've built aircraft wings since, well, the dawn of flight. Moving right along to Section 2, explaining HyTEM technology. All right, let's all put our aerospace engineer hats on for a second. The technology DLR has implemented here is called HyTEM, which stands for hyperelastic trailing edge morphing. Just think about a standard commercial airliner for a minute. When you look out the window, you see those rigid flaps and ailerons deploying on hinges, right? They're these segmented, clunky, separate pieces of metal or composite. Well, HyTEM throws that entire concept completely out the window. It replaces those conventional rigid flaps with a morphing composite structure. Instead of a hinged flap moving up and down, actually scratch that. It's not moving on a hinge at all. The actual trailing edge of the wing physically warps and bends to adapt dynamically to the local flight conditions. So the crucial question is, how on earth do they achieve this? The magic number here is 10. Across the span of this morphing composite wing, there are 10 specific adjustment points right on the trailing edge. And these points are manipulated by a series of distributed span-wise actuators. So instead of one massive hydraulic piston pushing a rigid flap, you have multiple precision actuators working together to bend this hyperelastic material. And they react incredibly fast, faster than a human pilot ever could, shaping the wing into the exact aerodynamic profile needed at any given millisecond. And you can really see the physical difference right here. Now, to make absolutely sure their data was rock solid, DLR actually fitted the Proteus drone with conventional composite wings first, just to gather some baseline comparison data. On the left side, you see the traditional approach: rigid flaps, segmented edges, and lots of mechanical hinges that create gaps. But on the right, the HyTEM wings. Because of those 10 adjustment points, warping the flexible composite, you get this completely smooth, continuous profile. No gaps, no hinges sticking out into the airstream, just a single, seamless surface reacting directly to the air. Which naturally leads us right into Section 3, aerodynamics and overall efficiency. So why go through all the trouble of engineering an hyperelastic wing? Well, it all comes down to one massive factor: drag reduction. Martin Radistock, he's the lead of the MorphAIR project at DLR, and he sums up the physics of this perfectly. He says, the continuous shape reduces profile drag. Lift, induced drag, and aircraft control can all be influenced in a targeted manner. Basically, the big takeaway here for us is that in traditional wings, all those gaps and hinges create turbulence, what engineers call profile drag. By eliminating the gaps with a continuous shape-shifting edge, the air flows so much more cleanly over the wing. Plus, by fine-tuning the exact curve using those 10 actuators, the aircraft targets and reduces induced drag, which is just the drag created as a byproduct of generating lift. Less drag equals massive improvements in overall flight efficiency, saving a ton of energy and fuel. But hardware is really only half the story here. Let's look at Section 4, the AI adaptive brain. Think about it.
Having 10 independent actuators constantly adjusting a flexible wing surface, yeah, that is way too complex for traditional flight control software to manage efficiently, let alone a human pilot. So DLR integrated an adaptive artificial intelligence system developed by one of their specialized institutes. This AI basically acts as the drone's central nervous system. During flight, it constantly compares the aircraft's actual physical behavior in the air against a highly detailed internal flight model that it was trained on previously. It senses the airflow, calculates the optimal wing shape for that exact fraction of a second, and continuously adjusts both its internal models and the physical wing itself. And this AI isn't just about maximizing efficiency, it's about survival. Let's cover Section 5, System Fault Tolerance. Imagine the drone takes some sort of damage midair, or maybe one of those actuators simply fails. A conventional system might really struggle with that, but this AI handles it beautifully in 3 rapid steps. First, the adaptive algorithm immediately detects a behavioral deviation. It instantly knows the drone isn't flying the way its internal model says it should be. Second, using just a tiny amount of sensor data, the AI reconstructs the surface pressure distribution across the wing to figure out exactly what the aerodynamic disturbance is. And third, this is the true genius part, it recalculates on the fly and optimally coordinates the remaining functional actuators. It actually reshapes the surviving parts of the wing to compensate for the damage, maintaining optimal flight stability. Now, the reason the AI can pull off this kind of midair save is all because of how it was educated. The researchers specifically fed simulations of damage and individual control surface failures right into the AI's model training long before it ever left the ground. It was essentially taught how to fly a broken aircraft. Unlike conventional flight control systems that rely on strict, pre-programmed rules, this adaptive approach makes the entire morphing structure incredibly fault-tolerant. So, how did this actually play out in the real world? Let's look at Section 6, Flight Results in Aviation's Future. The short answer? Spectacularly. The initial flights at Coxstead were a resounding success. DLR confirmed that the Proteus drone demonstrated full airworthiness with the HyTEM system. They successfully verified the incredibly complex integration between that physical morphing structure and the AI brain. They proved the aerodynamic potential, showing real-world drag reduction and boosted efficiency. And perhaps most importantly, they proved that this entire setup offers significantly improved fault tolerance compared to conventional rigid wing setups. But DLR definitely isn't stopping there. To prove this technology isn't just a party trick for lightweight drones, they are planning another major flight campaign this year. The target mass for the Proteus in these upcoming tests will be scaled way up to 70 kilograms. Pushing the weight up to 70 kilos, which is roughly the weight of an average adult, is absolutely crucial for an aerospace engineer. It's how you verify the scalability of the tech. They need to know for sure if those actuators and hyperelastic materials can handle the much heavier aerodynamic loads that come with a larger mass. And all of this incredible data being harvested from these flights, both the baseline composite data and the new HyTEM AI data, it's all feeding directly into a broader initiative called UAdapt. UAdapt is this massive project focused on designing the absolute next generation of unmanned aircraft wings. So the Proteus isn't just some cool one-off experiment. It is literally laying the foundational data layer for how the wings of the future are going to be engineered. Which leaves us with one pretty massive question to ponder. We are looking at a system that perfectly mimics the continuous, seamless adjustments of a bird in flight, managed by a digital brain that can instantly heal its own aerodynamics if it takes damage. If this adaptive AI and morphing wing technology can successfully stabilize and save a damaged 70-kilogram drone today, what will it do for the safety and efficiency of the commercial airliners you and I will be flying on tomorrow? It's a genuinely thrilling look at the horizon of aerospace engineering. Thank you so much for joining me for this explainer, and keep your eyes on the skies.